Okay, and welcome back to Algorithms Live. I'm glad you guys are back. It's been a nice break, but I'm happy to get back into algorithms. So should be a good episode. This week, I'm going to be going over this technique called DFS Lowlink or DFS Lowlinking. It's just really just a way to modify DFSs and get some more information out of graphs. So you can do it on directed graphs, undirected graphs, pull out a little more information from that. So this week's episode is going to be kind of nuts and bolts. I'll go over some definitions. I'll go over how to actually implement some of these things. And then next week, I'm going to show a bunch of cool problems that use these ideas because it interconnects with a bunch of other things. So if you already know this algorithm, then that's all I'm going over this week. And next week, I'll go over some more interesting properties and some other variants and neat things like that. But it is a fun algorithm to just implement and to reason about. It's got some basic graph theory and you can think through it. So without more delay, I'm just gonna run right in. And hello, everyone. So please, if you have any questions, write something in the chat. And yeah, happy to be back. Okay, so the first thing I want to talk about is some properties that you see in graphs. And we're just going to focus on two right now and then two related properties later in the video. So this first one is called cut vertex. Maybe I'll make the pen a little smaller. You'll also hear this called articulation points. Okay, so what's the idea here? So let's say I have a graph, something like this. So an articulation point is a vertex. When you remove it, it disconnects the graph in some way. So you'll notice I remove this, I end up with basically two lines going out like that. The graph may already be disconnected though. So sometimes you'll see a nice formal definition saying something like, it increases the number of components. So it's basically going to break off a piece of the graph. That's how you can look at it intuitively. And there's a related concept called cut edge. And this has another name, and it's called bridge. So you hear about people talking about the bridges in a graph. They're talking about cut edges. And the concept is very similar. You basically, if you cut one of these cut edges, it increases the number of components. That goes away. You remove it, you end up getting, you disconnect the graph in some way. Another thing you can be thinking about in terms of bridges. So if let's say you had a forest or a tree or something like that. So if you know you have a forest, then every single one of these edges in the graph is a bridge. So that could be a different definition for tree. So a tree is composed only of bridges. I like this kind of graph for testing. So you can throw a tree into your bridge checking algorithm. When we implement this later, that's what we'll do. And just make sure it's working. You make sure it just pulls out all the edges. But that's not sufficient to test that. You should also test things that don't have bridges. Okay, so let's start off easy. How do we find this thing? And so the first thing I'm going to do is just the most brute force thing that comes to mind. So if I want to find some cut vertex, probably the simplest thing that comes to mind is just remove each vertex and see if the number of components goes up. So you can do a component check with DFS or BFS. And the runtime here is you just try every single vertex and then do a V plus E DFS check and you get this runtime. Which isn't very efficient, but if the bounds aren't big, it's a good choice. There's also cut edges. You can do the exact same thing, try every single edge, and then just do a BFS or a DFS. So the reason I bring this up is this is really good to test against. So if you're having bugs in your code later when you implement it, and you want to just quickly know if your code's working and not have to reason through if these things are correct or not, just implement it this way, and that'll be a really good way to test your code, make sure it's working, and you can use it for other things. So we do, oh yeah, had a few questions on the chat already. They're asking about the subtitle option in terms of things that happen. Yes, the subtitles show up for the stream, I think, when it's available later, not during the live stream. But we'll see what happens. Yeah, I guess I am talking a little bit fast this week, but keep moving on. Okay, so this is our naive find vertex, find edge. But can we do better? And so better for me would be something like v plus e. And that's what we're going to try to do. So the first thing I want to just focus on is finding the bridges, finding these cut edges. Those will be a little bit easier than finding the cut vertex, and you'll see in a minute. But we'll just work on finding these bridges, and then we'll extend this idea to articulation points. So let's draw a graph. Looks something like that. So the first thing I want to point out, so let's put some IDs on these nodes. So the first thing I want to point out is every time you do a DFS, you get a tree. And so that's what we're going to do here. I'm just going to start from vertex 1, and I'm going to just do a regular old DFS that we know and love. So I'm just going to go down this left child down to 2. So my DFS is going this way right now. So you can kind of follow me around. I'll go out to 5, go out to 6, go out to 7. So it's an undirected graph, but I orient the edges the way I'm traversing them. I've already seen 5, so I come back. And I come out to 4 as bit as I can, and then come back. And then go out to 3. Then go out to 8, 9, go back out, and then to 10. So what you notice here is we end up having these tree edges when you do a DFS. These are the edges you actually explored. And yeah, so a DFS, anytime you do a DFS, forms a tree. So that's the very first thing I wanted you to be thinking about. But you notice when we do these DFSs, some information gets lost. There were some edges that we walked. We basically considered walking. So it was like this edge right here, or this edge right here. It visited something that had already been visited. So it's a good idea to think about, in terms of DFS, what are the types of edges that you can come across when you're doing a DFS? So we'll look at the 3 right here. So we have the forward edges. And so those are the tree edges that you just saw on the graph right there. So basically anything that forms my tree in terms of my DFS was a tree edge. But we also have edges called back edges. And so what those are is you're doing your DFS. And when you do a DFS going all the way out, you have a call stack in terms of what you visited. So I've already visited this node, this node, this node, this node. And then I end up hitting something else. It's on my call stack to still be exploring its other siblings in that DFS tree. So that back edge goes up the call stack to something that's already been seen. In terms of the tree here, so for example, when I was out at vertex 7, so actually I went around this way, 5, 6, 7, I started taking this edge back to 5. This would be a back edge. So that was something that could happen in terms of a back edge. And then we also have this thing called a cross edge. So this goes back on the same subtree. The one being explored. This one crosses subtrees. So I'll show you kind of what this looks like in concept. Let's say you're doing a DFS. And then you go out to the right here. You visit a node, and then all of a sudden you have an edge that goes across to some other subtree. That's what a cross edge, not very cleverly named, but it goes from one subtree to the other subtree, and you just cross over like this. So that's the third type of edge. If you're a bit perceptive here, you could also have edges that come down like this. So I'm doing my DFS and then I hit something that's forward like this as well. I also consider that a cross edge. So I lump those in with the cross edges. So some of you might think this is a bit different, but I only think about the three types of edges in terms of the DFS. Okay, so the important thing here that's kind of nice is in undirected graphs, you never have the cross edge. So this will never occur in an undirected graph. We only have to worry about forward edges and back edges in terms of our tree. The cross edges come up when you start having strongly connected components, searches, and directed graphs. So I'll show that in a later video. But right now, we only have to focus on these first two. So I can just delete this for now, get rid of this for now, and just focus on these first two and kind of see what happens in terms of our DFS and how things work. Okay, so let's modify our DFS and put in all these back edges and kind of see what is going on here. So I was doing my DFS out to 4 to 3. 3 had a back edge to 2. And 3 also had a back edge to 1. Something like that. Okay, and I think those are all my back edges. So what we want to do here is we want to find bridges. And you can see in the original graph, there are 4 bridges. There's this one, this one, this one, and this one. And we want to find these efficiently. We want to be able to, during this DFS, be able to find where those bridges are. Okay, so the idea here is we want to be able to cut some bridge and know that if this bridge went away, this subtree can't escape. So in other words, the name of the game here is to escape the subtree. So if I'm in a subtree right here, I'm considering exploring this subtree. As soon as I go down to 5, I won't be able to get out. So let's think about how we could get out of this subtree. Well, we can't take a cross edge because this is an undirected graph. Can't get out of the subtree that way. We can't take a forward edge because we'll go down further into our subtree in terms of finding our bridge, knowing if the edge we're exploring is a bridge. So the only way we can escape the subtree right now is to take these back edges. And so the back edge could be somewhere deep in the tree. So if we're, let's say right here, we want to know, hey, is this a bridge or not? Well, if I decide to cut it, I go down the subtree, I go down to 7 using forward edges, I can escape the subtree going up like this. So all we need to know in order to find a bridge is I'm at some subtree. Does there exist some node in here that I can walk down through forward edges and escape the subtree through some back edge? That's really all I need to know. So that's the name of the game here. So let's forget about the back edges for a moment. One really nice thing about a tree structure is you can do subtree aggregates. So if you go back, I think episode 1, I had the Christmas tree video, and we looked for the centroid of the tree. We found a centroid of the tree by storing subtree sizes at a given time. So what I'm going to do here is I'm going to have these subtrees hanging down like this. I'm going to store some aggregate information for the entire subtree at some node. So if I'm at this node, I want to know some information for this entire subtree. And that's going to be useful. And the thing I'm going to store for every single subtree is how far up the tree can I get using back edges from that subtree. And so what I'm going to do is I'm going to call that value a lowlink value. And that's where the idea of low linking comes into play. All right, so we need to have some metric to know how far up the subtree we can go. So I've seen DFS Lowlink implemented 2 different ways. One way is people store depth information. So they'll just store how deep everything is in the subtree as they're doing a DFS. That's perfectly fine. You can do that. Another thing you can do is you can store the pre-order numbers. So forget about the back edges for a moment. Just think of it entirely as a tree. And what you can do is you can store the preorder numbers of each of these trees. Something like that. And this will have much the same effect because we only worry about the back edges. So what we're going to do is we're going to save, for my preference for this video, you can actually implement it the other way using just the height information, is I'm going to use the preorder number. And the second value I'm going to save is called that lowlink value. So your lowlink value starts off as just yourself. The highest point you can reach in your subtree is just stay where you currently are. But then if you ever come across a back edge, then you look at the preorder number for that node. You don't look at the lowlink value, you look at the preorder number, because this could get up higher in the tree some other way. But in terms of using this back edge, take that preorder number and then min it with your lowlink. I'll do that here, and then I'll do that here. Okay, so now when you come across an edge like this, in terms of our search, and then here's my current lowlink value, if the lowest point I end up getting to is further down the tree than I am, then I know this must be a bridge. There's no way to escape the subtree. And that's all I have to do to detect if some edge is a bridge. So what I'll do is I'll just do a DFS down, see this back edge come up here. It's stuck in the subtree like this. And I can't get any higher. Once I hit enter this node 5, I can't get any higher up the tree. So this must separate something. So if I remove this edge, this tree can't escape. And that's all there is to it for finding the bridges. So you can look at some of these edges that aren't bridges, and you could write out the preorder numbers for each of these. So if I came out to this position right here, my preorder number is 3, but my low linking value is also 3. That means I can escape the subtree in some way. If I was considering this forward edge, so you want to consider the forward edge after you're done doing the exploration. That's kind of an important thing. But I just look at this low link value here, and I compare it to my preorder number, and I see that I ended up getting further up the tree than I currently was. So this edge doesn't separate anything. So that's how you find bridges. Okay. So let's look at articulation points now. So we're going to go do the same thing with cut vertex. And what I'd like to do is I'd like to be able to identify all cut vertices in our graph anytime I'm doing my DFS. And as it turns out, this is a little bit harder. I'll let you see why. So I'll be thinking about that. So I'll start off with my DFS. I'll start at node 1, go down to node 2. And I'm going to just be storing preorder number stuff as I go. So 1, 2, and so on. Maybe I'll fill those in after. So 3, 4, I end up with a back edge up to 2. So I get 4, 2, 4, 2. Oh, and 3, 2. Another thing too is when you explore your forward edge, your low link value gets minned with the low link value of that forward edge, because you're storing a subtree aggregate. You're storing for the entire subtree what's the lowest I got to. But then when you do a back edge, you update based off the preorder number. Okay, and this comes out to 2. So I've come down this way. And I'm coming back off my DFS, and my DFS now goes towards 5. So I explore node 5. Maybe I get a back edge to 1. So I get 5, 1. So this is why when you do your back edge off your low link, you only go off the pre-order number and not off the low link value. You don't want to take 2 jumps off a back edge. This is a good bug case graph. Catch a bug in your code. So I can go out to 6, go out to 7, then I have a back edge coming back. So I end up getting 6, 6, and then 7, and then I take this back edge and update off the pre-order number. So that's a 5, 5. And so I'm coming off the DFS. Every time I finish exploring a forward edge, the thing I look at is I say, this low link value, did it get higher up the tree than my vertex? So that's the name of the game here. So you still look at the destination of the edge going forward. So I'm doing a DFS. I'm at some node, and I've just explored a forward edge. This has some pre-order number. I want to know if I explore this entire subtree, can I avoid this vertex by going up the tree this way? It's kind of like the bridge case, because the only way I can escape the subtree is if I can get around this vertex. And so I just check in the subtree, can I take some back edge and get around this vertex? Does it actually separate anything? And then I'll know I'm a cut vertex. And that works fairly well. As you can see, I can just check the low linking value right here relative to my pre-order number right here. And if it doesn't get further up the subtree, if it doesn't have a lower pre-order value, then I know I'm a cut vertex. I've separated some piece of the graph. And I want to do this after every single edge exploration. So sometimes you'll end up with a component that gets further up the graph. You want to make sure that later on, if you do some other edge exploration, that you didn't also get trapped in the subtree. Okay, so it's looking good so far. So this works in the majority of cases, but it actually has a really big problem. So right now, the name of the game was if you were at some node, you wanted to know if you're a cut vertex, you explore down the subtree, and you consider, can I escape out this subtree, get around this vertex? This works extremely well, except for the case where you're the root node. Because if you're the root node, you don't have anything above you to escape to. That's the big problem here. We don't have some path above us to escape the subtree, and then I could be a cut vertex. In fact, I can still be a cut vertex as an articulation point. So let's take a quick look at a tree where this is the case, and a graph where this is the case. I have something like this. I could start my DFS right at this node. So maybe 1, 2, 3, 4, 5. I start my DFS here, and now I have a problem. So if I start my DFS at node 2, I wouldn't be in trouble. If I start my DFS at node 1, now I have a problem. So I go to node 2, go to node 3. I get up the tree like this. I go to node 4, go to node 5. I get up the tree like this. And you'll notice I separate these two subtrees. This subtree is separated from this subtree. But if I started my DFS differently, I would have identified this correctly as a cut vertex, because there'd be no way to escape the subtree. So this is a bit of a special case. So if you're detecting a cut vertex or articulation point, it works for every single vertex doing it this other way with the low length values. Except when you come across the root node, all you have to do to detect if it separates something is you count the number of forward edges leaving the root node. And if the number of forward edges is exactly 1, then you're not a cut vertex. So just write any, just do a DFS from anything that isn't a cut vertex, and you'll see very quickly that it doesn't have multiple forward edges. It's going to explore everything because it doesn't separate the graph anymore, and then come back and you won't have another forward edge to explore. But if it is a cut vertex, you've got subtrees that are separated from each other. And that's how you end up having a cut vertex. Okay. So that's cut edges and cut vertices. So what I'm going to do now is I'm going to take a break from explanation and actually just implement some basic DFS lowlinking. And then we'll get into the more complicated stuff, which is actually extracting some bi-connected components. All right, so figure out how I want to code this thing. So usually, talk implementation details. I make a graph class when I do something a little bit complicated. And that's going to be the case here. I'm also going to do something a bit strange here. And I'm going to make an edge class that's going to store some extra information on my edges. I'm going to keep IDs for all my edges. So I'm going to keep track of like all the edges that exist at any given time. And the reason I'm doing this is I want my code to handle parallel edges. And I want it to handle self loops. And I find that this is just the easiest way to deal with having self loops and parallel edges is just have IDs on your edges. And so you'll be able to test this code later, and you'll see that you can get it to work with in a bunch of different cases. So it should be pretty good. Yeah, I'm going to also use some hacky stack stuff. So if you want to see some gross implementation stuff that's good for competitive programming, that's what I'm going to do. Okay, so I'm going to make my graph class here. Sometimes I make these array decks. I'm making them arrayless here. Really just a preference thing, maybe a little bit of a performance thing in Java. You can just use a vector in plus. And what I'm going to do is this m value. So n is the number of nodes, m is the number of edges. So every time I add an edge to this graph, I'm just going to increment that counter. Just going to make a ij edge to be added. So adjacency, and you add edge j and then m. Every time I add an undirected edge, I have to add it both ways. And then I'm just going to keep this counter. And so this will just be helpful in doing a visited array on edges, which may strike a few of you as being a bit weird. But I prefer to do it this way. All right, so yeah, I guess I should read in the graph. So I'll make the graph code something like this. So I'm going to, standard graph problem says you take in the number of nodes, and then you take in the number of edges. Not actually solving a graph problem, so I can just do it this way. And everything's one index, so I'll be one index too, I guess. And I'll just read in my graph. And I want to do my DFS behavior. So basically what I'm going to code is a normal DFS, but I'm just going to add one extra thing. I'm going to return -1 if I haven't seen this node already. So it's basically just going to tell me it's a forward edge. In my DFS, I'm going to return the pre-order number, or my lowlink value. Pre-order number, yeah. I'm going to return my pre-order number of the thing I found min with the lowlink value in terms of the DFS if I end up finding something. So the way I'm going to write this DFS is I'm going to store what node I'm at. I'm going to store what's my parent node. I'm going to store what edge ID am I taking on this edge, forward edge or back edge. And so that's going to be fairly useful for me to get things right here. take a quick look at some stuff here. Maybe I don't need the used array here. Yeah, we'll try to have fun with this. Okay. I'm going to store some extra information on this graph. So let's put the graph here. I'm going to store pre-order number, and then I'm also going to store this lowlink value called low. Lowlink value. So basically, if I don't have a pre-order number for this node, so I'll just fill this initially. I'll use that fill pre-order number with -1. That means I'm using my pre-order number labeling as my visited array. So if you're curious about that, what I'm going to do is I'll just lowlink to my parent. So this basically means I'm a back edge right here. And if that's the case for me being a back edge, then I just return my lowlink value. So that's just the way I'm coding this is I'm lowlinking to the parent of my call. So if I'm a back edge, this might be a little bit weird. Let's take a look at this. So here's my parent is 7, and I'm taking a back edge up to 5. So this is node I, which is 5. I take this right here. So I'm going to save the lowlink value here as my pre-order number. And I'm going to take that mind with whatever my lowlink value was currently. So instead of doing it off the DFS call, I'm just going to do it as a base case to my DFS. OK. So now I loop through the edges. Should probably update my pre-order number. OK. So I'll do it like that. So if I've already explored this edge, this basically means I don't take an edge forward and back unless it's a parallel arc. And then I do my DFS. OK, so what I do is I run my DFS. And if I take it and it's a forward edge, then it'll return less than 0. So I should probably put that right here. So I'll return -1 if that's the case. So this tells me I'm a forward edge. And so I still have work to do if I'm a forward edge. So the two things I do if I just explored a forward edge is I update my lowlink value with the subtree's lowlink value. So this is me updating my lowlink values if I was a back edge. I still have to handle the case where I update my lowlink values if I'm a forward edge, because remember, we're storing subtree aggregates. So we need to know that this subtree, if I took this forward edge here, I take the min of this value and this value. Right? And so my bridges case is if my pre-order number ends up being the same as my lowlink value for my subtree, then I know that taking this edge must be a bridge. That's my bridge condition. So what I'm going to do is make an array list of bridges. I'll code my bridges this way. And that's the only check I need to make. So basically, this tells me if the low link value ends up being lower than my pre-order number, because it can't be higher because I set it as my pre-order number initially. But if it ends up being lower than my pre-order number, then I know it's a bridge. Okay, so then the only other weird case that I could possibly have is if the only other thing I have to figure out now is finding articulation points. So what I'll do is I'll make a Boolean array of vertices that basically keep track of if I have an articulation point or not. So finding articulation points is a bit harder, as I said. So let's add some stuff for bridges. And I'll show you how to do the art point check elegantly. Okay. So if you remember, there are two cases. There's the case where I'm the root node, and then there's the case of my search. And then there's the case where I'm not the root node. So the way I'm going to handle this is I'm going to write a Boolean called hasPath. Maybe I'll call it hasForward. And initially, I don't have a forward edge at all. And if I'm doing my DFS, once I've finished exploring the forward edge, I'll say hasForward equals true. So now I have a forward edge going forward. So there are two cases. So here's what I'm going to do. I'm going to use a ternary operator to make my life easy. If I is not equal to p, then I'm not the root node. And I can do my check for articulation point just to check if the low link value of the edge I'm exploring, if it ended up getting higher than what I currently am, then I have to be an articulation point, higher than my pre-order number. If it ends up being higher than or equal to. So in other words, it didn't escape the subtree. Otherwise, I just check if I have a path. Because I'll know that I'll have an articulation point if this ends up being the second edge that forward edge I'm exploring as the root node. So what you're seeing right here is this is the check I'm doing if it's the root node case. This is the check I'm doing if it's not the root node case. It just makes it a lot easier to implement just using that ternary operator for me. Now, I'm not making an array list of articulation points. This will actually return true multiple times potentially. This detection of articulation point basically just says I'm separating something. So if I end up with an articulation point that separates multiple components, this is going to fire multiple times. So keep that in mind. The reason I'm coding it this way is when we go over bi-connected components, you'll see that having this fire multiple times is actually desirable. So thing to think about. OK, and so that's low linking. See if we can get this to compile and run and try a pretty small graph. OK, so last thing I want to do is my graph might have multiple components. So it might be disconnected. So what I'm going to do is just the standard loop over all the vertices. And if the pre-order number is -1, in other words, this node hasn't been explored, that's when I do my DFS. So I'm going to do a DFS. I'm going to say myself as my parent, and my edge ID being the last number in the edge ID list is going to be the edge I'm exploring. So there's really no edge coming in off the root node. So that's the dummy case. And that's all I'm doing here. Okay, so that's my DFS. It has forward. Okay, so we'll do a simple check, put in some testing code. So I'll just grab my articulation points real quick. Should work, hopefully. Ooh. Into F. So no bridges and no articulation points. Works as desirable. Okay, so let's make a tree. 1, 2, 2, 3. Those are the bridges, and the center node. These are all off by 1 index. Oh well. But all the art points are 1. Let's make it a little clearer. I'll do everything by IDs. And everything's 1 indexed. So you can see it found both the things are bridges, and it found the articulation points correctly. In that case, it seems. Make a nice little fish graph and make sure the articulation points are working correctly. So we'll do 6, 6, 5, 6, 1, 2, 2, 3, 3, 1. And then I'll do 3, 5, 3, 6. Ooh. Oh, I forgot node 4. Okay. 5, 6, 1, 2, 2, 3, 3, 1, 3, 4, 3, 5, 4, 5. And so it found 1 articulation point, but it ended up finding the bridge. And then I can also rework this graph to, instead of the articulation point being node 3, I could do 5, 6. And you can draw this one out on paper and kind of see where I'm going here. 2, 3, 3, 1, 1, 4, 1, 5, and then 4, 5. And it should find node 1. So those were the 2 cases I was just testing. So it appears to be working on these articulation points. So you could try coding this one yourself, throw in more components and fun things to check, and get the articulation points. All right. So we have bridges, we have articulation points. Let's switch back real quick. And I want to talk about some component stuff, because that'll be useful. Okay, so let's talk about what K connectivity is. It's a pretty useful thing in terms of algorithms and competitive programming and all that. Okay, so let's talk about what K vertex connected even means. So there's this thing called K vertex connected. And so you can have a K vertex connected graph. So it basically means you have 2 properties. The first one is the graph has at least k vertices. And the second problem is it remains connected if so it basically tells you the fragility of the graph in some ways. So you have a graph like here, so a little bow tie graph. And this is two connected graph. No, one, this would be a one vertex connected graph. And the reason being is if I end up removing this vertex, so the reason it's not two connected is if I remove that vertex and all edges attached to it, the graph becomes disconnected. So that's what it means to be k-vertex connected. You can have a graph that's a little bit more connected. It's kind of a weird definition here. And you can have, in this case, this is at least two vertex connected because I can't remove just one vertex and break the graph into pieces. I think this might even be three vertex connected, this one I drew here. Any two vertices, I believe, I can't disconnect the graph. So it's pretty well connected. So what we're going to focus on are two vertex connected components. I also want to point out there's something called k edge connected. So a k edge connected graph, it's the exact same definition, except this becomes edge and this becomes edge. So it's, you have to have at least k edges. And if fewer than k edges are removed, then the graph still remains connected. So we care less in this video about what it means to be a k-connected graph or k-edge connected graph. We're actually a little bit more concerned about this thing called two vertex connected components. Okay. So a two vertex connected component, it's basically a, I'll use the word here, maximal subset. So as many vertices as possible of the edge set. So it's a subset of the edges in your graph such that the induced subgraph is two vertex connected. Fancy definition. I'll explain what it means. So what we have here, induced subgraph, all that is you take some subset of edges or nodes, and you basically just take what's necessary and left after you define those nodes. So in this case, like I take a bunch of edges, so I only keep the vertices around that are at the ends of those edges, and that gives me an induced subgraph. And that's what I'm doing here. Another thing that's really weird about this is an edge set. It's a subset of E, and it's two vertex connected. So this can get a little bit weird with the definitions. Sometimes you'll hear this thing called biconnected components. Sometimes you'll hear these things called blocks. Those are other synonyms. So you've probably seen biconnected components. And you've also seen, you can look them up and call them blocks. It can get very confusing because then you need something for two edge connected components if you take biconnected. So I'm going to avoid this definition right now. Sometimes in some literature, you'll hear these called blocks. This is probably the one area where the terminology is very confusing for me based on all the different sources I've read to explain this. Okay, so that's the vertex connected components. Let's take a look at a graph that has this. and we'll break it into vertex connected components. So I have a graph right here. And here's what I'm going to do. I'm going to put edge IDs on the edges. Right, something like that. So what should be my two vertex connected components? So I want a subset of the edges and it to be as large as possible. And I want them to basically, I don't want to be able to remove any vertex. So if I can remove one vertex and break apart that induced subgraph, then I have a problem. So it turns out the ones that end up having this property are these edges right here that will form one such subgraph. So E1, E2, E3, E4. And then I have the second one right here. So E5, E6, E7, and E8. And those are my two subgraphs. So the edge set over here and then the edge set over here. The other thing you should notice is there's an articulation point or a cut vertex separating the two maximally sized components. Another thing to point out, this definition is a bit wonky here, so I actually prefer other ones for this reason. But a single edge by itself, a bridge, if it's a bridge, it's in its own two connected component, or two vertex connected component. So if you ever have a bridge, you just keep it in its own component. And so what should happen is the union of all these components in these edge sets should be E. So you union them together, you should get the edge piece. Okay. We're just going to slide over here. And I want to talk about the second type of component. So we have two edge connected components. So what this is the largest, or I should say maximal, subset of vertices now. So this is a vertex set, even though it says edge here, so that's a bit confusing, such that the induced subgraph is two vertex connected. All right, so you can see there's some parallels with the definitions. Finding these is a bit easier. So let's draw a graph like this. We're looking for vertex set, so I'll label each of the vertices with a label. Finding them is a lot easier. All you have to do is you cut all the bridges, and what you're left with when those bridges are gone is you're left with connected components. Every single one of these connected components forms a two vertex connected component. Something like that. So here are components here. Similarly, let's say I had something else in the graph. So let's say I had this shape in the graph. This would be one big two connected component because there's no bridges in that. Even though there are two vertex, or yeah, this would be one big two vertex connected. Oh, I messed up this definition. This should be edge. But this would just be one thing, even though there are two vertex connected components, one here and one here. but the nodes here form an edge connected component, two edge connected components. Okay, very good. So finding this, once again, is easier. All you have to do is you cut all the bridges, so you don't have to physically remove them from the graph. We stored edge IDs. Just keep a visited array or a marked array, basically say what the bridges are. And then you can just do a DFS and ignore any edge that ends up having a edge ID that's a bridge. You just don't cross it. You can just do your normal DFS, BFS. You can extract these components very easily. Finding these over here are a bit harder. So that's one thing we're going to focus on is finding those in a minute. Before I do that, I actually want to go over an alternative definition for the two vertex connected components and two edge connected components. So these are the alt definitions. If you want to do some reading later, the generalization of these definitions is called Menger's theorem. So you can do some expanded reading on this a little bit later if this is something that interests you. But if you have a two vertex connected component, this is an equivalent definition, so it goes both ways. So all pairs of edges have two vertex distinct paths. Between them. So basically what this means is if I grab one of the edges in the two vertex connected component and grab another edge, I'll be able to find a vertex path here, and they won't ever have to share a point. And so I end up getting something like this. And basically all this means is you can form cycles. And in other words, you can form cycles between any two edges, with one exception. If your two vertex connected component is a single edge, then this holds vacuously and there's some weirdness there. So you can't form cycles with just one edge. But all others you can. So that's good to know. We also have the two edge connected component. And so what I have here is all pairs of vertices path between them. So with that, I can take any two vertices and I get an edge distinct. They can share a vertex between them. That's allowed, but you can't share an edge between them. So they're edge distinct, which is kind of neat. So what this means is you can form circuits. So when you have these decompositions, they're very nice. This one is very nice for dealing with cycles. This one is very nice for dealing with circuits. And when I go over some neat problems next week, you'll actually see I'll be able to decide which one I need based on, hey, I need cycles if I have two vertex connected components, or I need to do something with circuits, I need the two edge connected components. Or I might need the bridges, or I might need the cut vertices. It really just depends on what I'm doing, what kind of problem I'm solving. Okay, so let's go back. One thing we need to find is these two vertex connected components. And I just want to draw a graph that makes this hard, so you get a good idea of why this is tricky. So we know that when you take bridges and cut them, you get the two edge connected components very easily. But when you take articulation points and cut them, so you can see what the articulation points here are, we end up having these really weird problems. So remember, it's an edge set. This is one that's one two connected component. That's another one right here. Another one right here. Go with yellow, sure. Another one right here. Run out of cool colors. White, sure. And then this one right here. But notice when I cut these articulation points, it cuts both these articulation points. This edge is kind of isolated, yet this is two vertex connected component right in here. You take the induced subgraph of these four edges, you won't be able to remove a node and disconnect it. So you can see how this makes it a bit tricky to find. You can't just cut the articulation points and then see if the edges can reach each other. That doesn't quite work out. It works out for every component on the outside in this case. This is a very good testing graph for that reason. Okay, so how do we extract the two vertex connected components if this is tricky? All I'm going to do here is I'm just going to modify my DFS. And I'm going to modify it by using a stack. So my solution here is use a stack. And I'm just going to keep all the edges that I'm exploring so far on the stack. And then when I end up getting time to know that I need to extract a two vertex connected component, I just pop them off the stack and group them together. Okay, so let's take a conceptual look at what I'm going to do. I'm running my DFS. I come across a forward edge. I get some node here. And I'll be searching around, and I'll find that I can't escape this subtree. So what's going to happen here, remember, I get multiple detections for my DFS. It's going to say, hey, this is an articulation point, and this subtree can't escape. What I'm going to do is I'm just going to pop off everything off my stack. So I'm going to have a stack of edges, an edge, an edge, an edge, an edge, an edge. And here's the forward edge that I'm exploring right now. This is F. So what I'm going to do is I'm just going to group all these edges together and say that's my two vertex connected component because I couldn't get anything out. Okay, so the stuff down here is further up in my DFS. And then you might think, well, what if there was another subtree down here that also had a two connected component? How do I deal with that? Well, if I'm popping them off every time I find an articulation point, these will have already been popped off the stack, and I only have to care about the subtree that exists currently down here. So all my edges are going to be grouped together that I've just explored. You also throw back edges on these stacks. So you throw all your forward edges. You want to throw the back edges too, so that that'll come part of the component. And that's what we do is we just pop them off and then we keep popping them off until we hit this forward edge again. That'll give us exactly what we need. Okay, I'll just run through a quick example. Draw a smaller graph. This will be my graph. And I'll do E1, E2, 3, E4. Move that over here. So before I begin, all right. So let's start a DFS. I'm going to start with node 1. That sounds viable to me. So I'll start at node 1. There's node 1. I'll do pre-order and post-order in the same color so I don't have to keep switching between them. And what you're going to notice over here is this will be my edge stack. Okay, so explore here, node 2, explore node 3. So I get E1, E3, and then E2 get pushed onto my stack. And this ends up being 1, 1, 2, 2, 3, 3. Okay, so now I get a back edge coming back. This low link gets updated to 1. I continue on with my DFS. So I end up exploring E4. So 4. And then 6. It's going down. So 4, 4, 5, 5. And so when I hit node 6, I can go 2 ways. I could go this way, or 3 ways. I could go this way, or I could go this way. You should try running this example by hand both ways. I'm only going to do it one of the directions. So I'll go down E9 right now. So 6 goes to 8. So this is 6, 6. And then goes to 7, which is 7, 7. And then I get a low link edge back to 6. So I should be pushing these edges on the stack. So let me go do that real quick. So I have E4, E5, E9, E10, E8. And I got my back edge coming from node 7 back to node 6. So I update my low link value to 5, update my low link value to 5. I come back here. I hit this node. As soon as I hit this node, I know I'm at an articulation point. These two values are the same. If they weren't the same, I wouldn't be an articulation point. I just finished exploring this edge. That edge was E9. There's my biconnected component. So what I'll do is I'll just keep popping them off the graph until these edges match, and I'll put them into one biconnected component. So I'll get E8, E9, and E10 all together. And I pop them off the stack when I find them. So that very first edge, this E9 that was on the stack right here, is sometimes called the root of the biconnected component, or two vertex connected component. So you'll notice that they're just grouped together that way. The important thing I wanted to point out was you'll notice that E4, E5, E6, and E7 weren't all on the stack when that happened, yet they make up one biconnected component. So if I went the other way, they would have been grouped together, and then I would have explored this differently later. But now I'm going to start doing my DFS continued, coming back off that search, and I'll search out here to node 5, and then 5 will low link back to node 3, something like that. So now you'll see my E6 and my E7 all still get grouped together. So this is 8, 3. This gets grouped back together as 3. Notice I failed my articulation point check now. So I have to find that articulation point right when I explore this edge, because that's when I knew I separated something. I don't separate this group from anything, so I'm fine. So I come off that check, This becomes 3. Yeah, I guess I'm having something like here. There might be a bug in my code actually, but we'll see. This ends up becoming 3, 1. All right. So there's no way to escape this subtree. So now I can look at this edge right here, which was E4, and I extract the next one. So E4, E5, E6, E7, something like that. And then I come all the way up my DFS and I'm done. So I end up hitting this last DFS. So what'll happen is if your root node is not, or if you end up at the end of your exploration with the root node, you should have one component left on the stack because it's not being separated from anything. It's just the one piece that was left after everything else got separated. So this is your last biconnected component. So I end up with just E1, E2, and E3. And that's my bi-connected components. All right. So we're going to go back and code this thing. It's just going to be a modification to our DFS. All we're going to do is anytime we end up hitting an articulation point, you detect an articulation point, something's getting split up here in terms of the subtree. That's when I'm going to pull off these edges off this stack, and that's going to tell me exactly where my bi-connected component is. Yeah, it was based off the lowlink and the pre-order number. I just misspoke. So no bug here. Okay, so to make my life a little bit easier, I'm going to make a helper function because I actually have to call this thing in two places. So that'll make my life easier. What I'll do here is I'll have an array list of integers, and I'll call make component. I'll pass it an ID. And so the way this function works is it's going to peel things off my stack of edges until I end up hitting this ID. And that'll be the very last edge that gets peeled off. So it was basically, this is the root of my bi-connected component, is this edge right here, that's ID. And I'm just going to pull things off the stack until I get there. I need to also add a stack to my code. So I'll do that here. I'm going to do the cheap stack. So I should tell you a bit about how this thing works. It's easy to implement a stack as an array if it's an array of integers. You just make node 0 be the number of things in the stack, and it becomes your stack pointer. And then everything else is a piece of the stack. And so that's the version of the stack I'm going to use here. It's going to be a bit strange, so look out for that. So let's see. I'm only going to add just enough nodes to the stack just to live a tad dangerously, I guess. So stack equals new int m plus 2. So add a little bit of buffer room. Okay, so I'll keep a edge stack. So let's start off with the easy piece. So I'm doing my DFS calls. If I come off my DFS, if there's something on my stack, so I don't know what the edge is going to be, so I'll just do the dummy edge. Oh, and the dummy edge might be on my stack, so I'll do it that way. My stack is 0. So I'll clear my stack off. Make sure there's nothing left on the stack. Let's start putting things on the stack. So if I do a DFS, it's either a pre-order, it's either if I'm at this point of the code, it's either a forward edge or a back edge. Both cases, I want to put it on the stack. I only want to put it on the stack if I haven't seen this edge before, though. I could try exploring this edge backwards, and things could be messed up there. So this is where I start bringing in my used array. So I'm going to have a used array. And this is an edge used array. Have I seen this edge before? So if I haven't used this edge ID before, then now I've used it. And I need to push this edge ID onto the stack. And so if you're doing the poor man's stack, this is what you do. You do a pre-order op on the stack, the bottom element of the stack. And then you just store whatever ID that is at that operation. So this is a push onto a stack. So this is kind of like hacky code, but I like it for some reason. Okay. And that's all you have to do for edges getting pushed onto the stack. What's nice here is this handles parallel arcs very well. So it's good to know for that. Okay, let's actually code make component. So this is pop off the stack. All I'm doing here is I'm just looping until the top node of my stack. So this is a peak operation in terms of my weird stack. And I basically just look at this ID and I make sure that I haven't hit the last ID. And then I keep popping things off the stack until I get off to my last node. The way I'm coding this, though, that's a bit strange. Then I'll just return the component. The thing that I'm not doing with this, though, is I'm not adding the last node off my stack. And the reason I'm doing that is on the very last DFS, what I'm doing is I'm pushing this dummy node M, or this dummy edge M with the way I have this coded onto the stack. And I don't want that to be in my component set. So that's how I'm handling this code-wise. So you could code this a little bit differently and probably avoid that step. So I'm also going to keep a record of all my bi-connected components. So I'll add the component to that. So let's make a record of bi-connected components. Call that comps. Okay. So let's actually do the add of components. So as soon as I find an articulation point, remember this will get called multiple times with multiple explorations. This is when I call make component on the edge ID of what I just explored. So I found something that got separated from the graph. And then once I'm done doing that component, I'll just add the last edge off the top of the stack. So this is the case where I add that very last forward edge right here. And then I just throw away the thing. So that's why I'm returning this component. So I call make component. It adds everything but that last forward edge. And here I'm adding the root of the bi-connected component. Just one small change here. And then I just look at my changes outside my DFS. I should also probably say I haven't used the dummy edge. So if I have multiple components, then that will be a problem. Okay, let's see if this thing compiles. Should have drawn out my graph. So I'll write that down real quick. Make sure it extracts the same thing. So I'm going to actually run this example, but on the graph that you see here. So let me write that down on paper, and then I'm going to make that a test case. Let's see, we have 8 nodes. We have 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, 10 edges. So I have an edge from 1 to 2, an edge from 1 to 3, 2 to 3, 3 to 4, 3 to 5, 6, 5 to 6, 6 to 7, 6 to 8, and 7 to 8. Oh, I should have been adding these in order. So 1 to 2, 1 to 3, 2 to 3, 3 to 4, 4 to 6, 4 to 6, 6 to 5, 5 to 3, 6 to 7, 6 to 8, and 7 to 10, and 7 to 8. Okay. Those are all my edges with my edge IDs. Okay, so I should get 3 components out of this, and they should match up with the sets that I have here in terms of my testing. I'll call that test 1. Again, the code. All right, I need to make my used array. Okay, it would help to print out the components, though. Yeah, I should probably also add 1 to all of these because they're not 0 indexed. That should be good. Okay, and this will print out all the components. I should also say how many there are. And this should match up. So remember, I found 9, 10, 8. So E9, E10, E8, E7, E6, E5, E4, and then E2, E3, E1. You definitely, if you want to test out this code, make sure it's really working. The best ones to check, this graph is fantastic. Run it on an articulation point, run it on something that's not an articulation point first. To make sure to test to make sure all this code is working for you. Try doing the DFS when you have multiple components. The graph might not be connected. You want it to be resilient to that. The last few cases are you want to also do a single edge case. So we'll do that real quick. So we'll do a test. New Q1. You'll notice the 2 connected component was just this. But we also want to do, and you'll notice my code even works when they're parallel arcs. Will be extra fancy. And it also works on self loops. So you want to make sure that the code can be that resilient, because it's a real pain to actually have code that doesn't handle self loops and have to pull them out manually if you're doing a problem, something like that. This code, written using the edge IDs and doing things with visited arrays, basically just makes it so you don't have to worry about those cases. And so having less weird cases is better. All right. And so that's it for this week. And so I'm glad to be back. I'm glad so many people were tuning in and checking out this episode. I'll return next week. Next week, in my opinion, will be a lot more fun, because I'll be looking at these decompositions based on the two vertex connected and two edge connected components. And I basically will get to show off a bunch of cool problems. There's some that there aren't too many DFS Lowlink type problems out there, I'd say. But when they come up, there's some, I feel like they're a lot of fun to solve. And there's some really interesting ones. So I just picked a few of my favorites. I'm just going to be going over that. And I'll be going over some of the decompositions. So I think it should be a good episode next week. So thank you, everyone, for tuning in. And I'll see you next week.